Our group is static prosthetic testing, and I am Nathaniel Vogel.
My name is Sean Farrell.
My name is Nathan Trudeau.
My name is Callum Silvestrini.
My name is Spencer Plum.
And I am James Tumia.
Prosthetic pyramid connectors are a vital interface component that ensures alignment and stability between the socket and lower limb prosthetic devices. However, they pose significant challenges, particularly for patients in underserved or low-resource communities. One of the primary issues is high cost. Traditional pyramid connectors are typically CNC machined from stainless steel or titanium, which makes them strong and reliable, but also expensive. For patients without sufficient insurance coverage or in countries where prosthetic care isn't publicly funded, this cost becomes a serious barrier. Additionally, these connectors need to be replaced semi-regularly due to wear, corrosion, or changes in the patient's limb alignment or residual limb volume. Each replacement not only costs money, but also requires access to a prosthetist, which isn't always feasible. This brings us to another critical issue, the shortage of orthotics and prosthetics professionals, especially in rural or underserved regions. In some developing countries, there may be only a handful of certified prosthetists serving entire regions. As a result, many patients wait weeks or even months to receive new parts or adjustments, leaving them effectively immobile. And even when professional care is available, traditional manufacturing methods are a bottleneck. Pyramid connectors are often made in centralized facilities and take significant time to fabricate and ship, especially when custom fittings are required. This delay disproportionately affects patients who cannot afford to wait, whether due to work, school, or basic mobility needs. In short, the current system is not scalable or sustainable for the populations that need it most. There is a clear and urgent need for a more efficient, accessible solution. Our objective in this project was to explore a lower cost, more rapidly deployable solution to traditional pyramid connectors using 3D printing as a manufacturing alternative. 3D printing offers several advantages. It allows for local, decentralized production, reduces material waste, and enables rapid iteration and customization. We focused on additive manufacturing to determine if we could produce connectors that meet mechanical and safety standards while drastically reducing cost and lead time. To do this, we tested a range of materials across different mechanical properties and print methods, including PLA, PETG, nylon 6 carbon fiber composite, and stainless steel. As shown in the images here, we use commercially available filaments such as PACF carbon fiber reinforced nylon from Bamboo Lab and PLA from Hatchbox as a baseline comparison. The end goal is to develop a 3D printable pyramid connector that can be fabricated locally, affordably, and quickly, with mechanical performance on par with traditional designs. This could drastically reduce both costs and turnaround time, and more importantly, expand access to mobility solutions in communities that currently face long delays or total lack of care. By reducing dependency on centralized manufacturing and specialized labor, we hope to empower clinics and NGOs in underserved areas to respond to patients' needs more effectively, ultimately improving quality of life and independence for prosthetics users.
In this experiment, we aim to test the yield strength of various materials by applying a bending moment to the pyramids. We began by creating pyramids using different materials, including PLA, carbon fiber reinforced nylon, stainless steel, and PETG. These materials were chosen to explore how different strengths and properties affect the performance of the pyramids under stress. Next, we fabricated a testing apparatus to fit within the load frame, which was specifically designed to apply a bending moment to the frustrum of the pyramid. Using the load frame software, we created an altered tensile test, which allowed us to accurately apply and measure a bending moment on each pyramid. All the materials were printed and fabricated according to their specific orientations, and we made sure that all the parts for the load frame apparatus were oversized to ensure that they would not break during testing. Once the pyramids and testing apparatus were ready, we used the load frame to apply the bending moment to the frustrum of each pyramid. This testing setup allowed us to simulate real-world stress conditions and measure how each material would respond. Displacement and load data were recorded and then carefully tabulated. The collected data was analyzed to calculate the yield strength of each material, which is the point at which the material begins to deform plastically. This analysis was critical in determining whether any of the testing materials could serve as a suitable replacement for traditional pyramid materials. The data was recorded using the Blue Hill software preloaded onto the computer. which directly interfaced with the testing apparatus. Afterward, the raw data was exported into a flash drive for further analysis, and from this data, we are able to calculate the yield strength of each material and verify their suitability for this application.
Now, let's go over the procedure that we followed for testing the pyramid connectors using the load frame. We started by recording the weight of each part to ensure consistency across samples. Next, we attached the top and bottom parts of the mounting bracket to the load frame. Then, we bolted a pyramid connector to the bottom mounting bracket, securing it in place for testing. Using the load frame, we applied force until the pyramid began to deform. At that point, we paused the test. Next, we recorded the yield strength, the stress at which the pyramid began to deform, and documented the data. Following that, we resumed the test and continued applying load until the pyramid ultimately failed. At failure, we recorded the ultimate strength, which is the maximum stress the pyramid could withstand. We repeated this process for each pyramid sample. After all tests, we compiled the data into a table for easy comparison. Finally, we analyzed the results to identify trends in strength and performance across different pyramid designs. Next up, we have our equipment. The first item listed is the Instron 5900R, and this was our primary testing machine. It was a load frame with a load cell that had a 100 kilonewton capacity. Next up, we have our Bamboo Lab P1S 3D printer. This printer was what we used to fabricate some of our parts. Next up, we have Pittsburgh digital calipers that we use to take the dimensions of various things, including the load frame that, so we could make a proper mount for the test. And then finally, the SLS printer, which was used to make our stainless steel pyramid connector.
So we went to the schedule. The schedule, we use the Gantt chart to properly show the progress and we want to get the report done and the project done. But unfortunately, due to setbacks with snowstorms, breaks, and teacher meeting times, this was soon thrown out very easily in the first few weeks. Now with the budget, we procured a table with showing the parts we used, the materials, and the cost that we spent on the project. Thankfully, the most expensive part, 316 stainless steel L pyramid, was donated to us by the school, but everything else we have to procure personally through friends, associates, or group members to help bring this together. And now for risk assessment. In the risk assessment, we put up a polycarbonate barrier between us and the load cell to make sure that if there was any catastrophic failures between the part and the apparatus, that we would not be harmed in the taking of the process. While during the process, we also wore safety glasses to make sure that if there's any shrapnel or parts from the apparatus or the load cell, that they wouldn't hit us and damage us in any sort of way. And then for the fittings, for the apparatus insert, we used a sander to sand down the bottoms to make sure they fit evenly, that they could slide in and slide out with no issue.
Now, here's a video of our test. Sped up, of course. This is over the course of almost an hour.
Now let's take a look at the results. As we can see, this is a table composed of all the materials that we were able to test with the load cell. As you can see, we were able to make different orientations with the PLA pyramid connectors, which in the end did have an effect on the total load the pyramid was able to withstand. With a vertical orientation, the pyramid was able to withhold a greater force. As you can see, our stainless steel 316L pyramid was able to withstand a total force of 2,470 newtons. As shown below, here are some graphs that were able to be created that show extension versus load. We came into some trouble when we tested the carbon and the steel pyramids. This was due to memory storage issues. Since we were taking so many data points, we had to stop and restart the same trial, which caused an error in the system, which is shown by the jumps in the graphs. we can see the same for the stainless steel graph here. And then lastly, shown below is a bar graph with all the materials with the maximum load of each material that was able to withstand. No, these other materials in the end aren't a suitable substitute for stainless steel.
So here are some of the main issues we ran into during testing. These created uncertainties in our results and are definitely things we'd want to fix in future setups. First off, the top part of the catch mechanism was pressing against the pyramid itself, which may have added extra stress or interfered with how the force was applied, which could throw off our results a bit. Also, our sample rate was way too high, especially during the stainless steel test. We ended up with an overwhelming amount of data, which made analysis more complicated and introduced noise we didn't really need. The machine would sometimes randomly stop mid-test, saying it had run out of room for data. So we had to pause and restart tests, which led to gaps and some lost data. For both carbon fiber and stainless steel, we noticed that instead of cleanly bending at the expected location, they started deforming near the top of the frustrum. That made it hard to generate the kind of bending moment we were aiming for and suggested some misalignment or setup issues. Finally, as seen in the picture provided, the bottom bolt slipped during the stainless steel test, which likely shifted the load path and reduced the accuracy of the test results. So overall, we still got meaningful data and were able to draw solid conclusions from the testing. These uncertainties just highlight a few key areas where we can improve the experimental setup moving forward. To conclude, our testing revealed some clear and important differences in performance between materials and print orientations. PLA and PETG, while inexpensive and easy to work with, failed at relatively low forces, under 40 newtons, which makes them unreliable for real-world prosthetic applications. The carbon fiber reinforced nylon 6 performed better, managing up to 78 newtons, but still fell well short of the strength needed for load-bearing components in a prosthetic limb. On the other hand, the stainless steel pyramid connector printed using selective laser sintering performed exceptionally well. It withstood 2,470 newtons before deforming, and importantly, it didn't fracture at any point. This result supports our original hypothesis that SLS printed stainless steel could meet the static strength requirements outlined in ISO 10328. It also gave us a real sense of what's possible when advanced manufacturing techniques are applied correctly. Another important takeaway was the impact of print orientation. We found that vertically printed samples were around 30% stronger than those printed horizontally. That's a significant difference and something that designers and engineers will need to keep in mind when optimizing parts for both strength and reliability. However, even with that technical success, there are some practical limitations. SLS printing is expensive, time-consuming, and not yet widely available, which makes it difficult to scale up for mass production, especially for communities that need low-cost solutions the most. We also encountered a few challenges during testing that introduced uncertainties into our data. The testing apparatus sometimes pressed into the samples, parts slipped during loading, and we ran into some issues with data collection that interrupted tests midway. These made it hard to get perfectly clean results, but they also gave us valuable insight into how we can improve our testing methods going forward. We operated under a few key assumptions, such as assuming that static strength was the most important performance factor. But in real-world scenarios, components experience repeated loading, impacts, and long-term wear, so future testing should include fatigue and cyclic loading studies to better replicate actual use conditions. Looking ahead, we think the next steps should focus on making the printing process more efficient, testing other affordable high-strength materials, and running additional trials that test durability over time. There's also potential to refine the geometry of the connectors to optimize both performance and material use. In summary, while we're not quite at the point where the 3D printed connectors could replace traditional ones in a clinical setting, our work shows strong potential. Metal 3D printing, especially using SLS, could become a key tool in making prosthetic devices more accessible, affordable, and quicker to produce for people who really need them.